In the previous lecture, you are struck with the memory disambiguation. In this memory disambiguation, let us just consider the example, and after that, we'll see the definition of memory disambiguation. Let us consider a for loop. In the for loop, the R1 is initialized with 0. Then, it enter into the body loop here, and first it calculates the effective address of this the value, and then we assign 0 into this effective address. So then the equivalent assembly code for this for loop, you just consider that first we are assigning r is equal to 0, and then we enter into the loop of the body. In the loop of the body, first it is going to calculate in this instruction. If you observe, it first calculates the effective address of your R2 plus your R1 multiplied with 4, and once that effective address is calculated, then we assign 0 into that particular location. And after that, once this instruction is executed, then it go and do the auto increment, so that we are adding the add operation, or add instruction is executed, that R1 plus your 1, and the value will be stored into your R1. And once it is incremented, then the comparison operation will be take place, whether the R1 value is less than 10 or not. If it is true, then it directly jump to the target address, your L0, and start executing this loop. So in this case, what happens, for every value of your R1 is equal to 0, your R1 is equal to 1, your R1 is equal to 2, your R1 is equal to 3, and so and so up to your R1 is equal to your 9. For every iteration, what happens, first it evaluates from here, it evaluates the effective address, that is your R2 will be added with, first it is R1 is 0, so 0 multiplied with 4, it will give the 0. Once this effective address is computed, then the 0 assigned to this. In the next iteration, your R2 value will be added with the 4 bytes, that is R1 is 1 multiplied with 4, that is 4, and then the 0 assigned. And in the next iteration, your R2 added with the R1 becomes 2, so 2 multiplied with 4, it becomes 8, and then assigned 0. And in the next iteration, your R2 multiplied with your 3, then at 12 it assigns 0, and this at the last iteration, your R2 added with your 9 times multiplied by your 4, that is your 36 bytes, and then assign 0. So from here it is clear that from the previous effective address, the next effective address is just 4 bytes away, and from previous one, the next effective address is just 4 byte away. So, and this, from this example, we can define that the memory access needs this effective address value. But do we need to always wait for the calculating this effective address to be computed to do the memory store? Means, can we predict in the future memory address? Means, from this example, it is very clear that every new effective address is just 4 bytes away. So in that way, we can predict. That we call the definition as the memory disambiguation is a technique to execute the memory access instructions speculatively by just predicting the memory address of that access just 4 bytes away from the previous one. So what is the benefit of this memory disambiguation? Means it issues the memory access as early as possible, and it allows more overlapping of memory access, and it reduces the compute, or it eliminates the it can reduce the every time go and calculate the effective addresses R2 plus your R1 multiplied by 4. So every time this computation is required. So if it is speculatively predicting that from the previous effective address it is just 4 bytes away, so this computation is reduced or eliminated. Once this computation is eliminated, the performance of your CPU will be increased. So generally, the benefit of this memory disambiguation, which allows more in the out of order instruction execution, so that we have seen that if there are some instructions we have observed in the examples, that instruction 1, your instruction 2, your instruction 3, your instruction 4, and if there is no dependency, then this out of order instruction happen, that the instruction 1 and instruction 2, 3 executed in a separate way, and your instruction 2 and your instruction 4 executed in separate way. We call this concept as your out of order instruction execution speculatively, and this is usually the memory disambiguation is only the out of order processors. Out of order processor. So now let us see, if the prediction is wrong, suppose if the prediction is wrong, that the every time the new effective address which is calculating is just 4 bytes away from the previous one, means if that if it is an incorrect speculation, then in that case how to handle this read memory access and write memory access, means just the procedure which we followed in the pipelining, that flush the memory. But here in read memory access and write memory access, the actual data never loads into the real registers. It always goes and load into the temporary register. If the prediction is correct, then it load into the actual register, real register. If the prediction goes wrong, then it can simply flush that value from this, that loaded data from the temporary register only. It will not take place in the real register. So same thing happens in the write memory access also. It will write always in the buffered temporary memory, that interstage buffers which we use. And if the prediction is correct, then it will write into the memory speculation. If not, then it will simply flush it out. So the wrong data dependencies, like we have seen in pipeline, have to be flushed, and the wrong results have to be discarded from the memory. So this is the concept of memory disambiguation. Then in this speculative execution, we are simply assuming that next the instructions will be taken or not taken. So based on we have seen this 2-bit saturating counter for branch predictions also. We have seen that the next branch will be taken or not taken. If it is taken, then okay. If it is not taken, then in that case we flush the data. But in that, by assuming that the next instruction will be selected or taken, means there will be some security implications are there. So what are those security implications? In speculative execution is an optimization technique where a computer system performs some tasks that may not be needed actually, or should not be executed. So in branch prediction is a type of your speculative execution, that the branch will be taken. In that prediction, after that, after calculating the effective address at the execution stage, it comes to know that actually this branch is not required to take in. Then we are flushing it out. But actually we are assuming that it is taken. So in that case, how it is going to be create some problems, or create some security implications. That means the speculative execution is essential in modern processors, since they are crucial for the performance. But it was until half of 2017 that we learned that there are some implications of the security impacts are there from this speculative execution. We named them as your spectre and meltdown vulnerabilities. So what is this spectre vulnerability? That means before taking any branches which are going to be predicting that the branch will be taken or not taken, branch will be taken or not taken, it must go under the code that the security check must go under the security check, and if it is passed, then the access the sensitive data. If it is not passed, then that branch is not going to be taken, and in that It will not allow to access any sensitive data. So normally the sensitive data can only be accessed if the security check is successful. However, with speculative execution, some sensitive data may be accessed before we know that if the security check is passed or not, because we are just predicting that the branch will be taken. So when the sensitive data is read into the cache memory from your main memory to, when you are reading from your main memory to your cache memory, the cache memory. So when you are reading, that time you don't know that whether that branch is going to be taken or not, and whether it goes through the security, whether the branch passed the security check or not. So in that case, when the sensitive data read into the cache, the separate the side channel attack will happen. Separate side channel will happen is the used to access this sensitive data. So what is that? This is a security check for suppose program counter 1, and same kind of program counter 2 will also have the, and for another branch that will hold the address of the next branch, and in that also it will write that if the security check is passed or not passed, and then it access the sensitive data, So in that case, the attackers will train the branch predictor that this branch will always going to be taken, but actually this branch should be taken. So this is a copy of the original branch. Okay, so from that, it will always go and pass this security check and try to access the sensitive data from this cache memory. So that is, the attacker can train the branch predictor to always predict true for the if branch, and recall that the branch predictor only uses the lower bits of your program counter. As we have seen that the program counter, it will check only the lower 12 bits to predict whether the branch will be taken or not taken. And from this 12 bit, it always, when it goes to your branch history table, the branch history table, by using these 12 bits, whatever the branch is there, it's set always taken, strongly taken, that can be set. So the attackers can find another branch instruction whose PC has the same lower bits as this if branch, and the attacker can then train the branch predictor to predict always taken by letting this second branch instruction be taken for several times. So that is the vulnerability of this branch prediction or security implications in this. We call this kind of vulnerability is named as your spectrum. And similarly, the meltdown vulnerability, which is similar to your spectro, but in spectro, it is worked on the security check, that program, but whereas the meltdown, it is performed by the hardware. So when accessing the OS kernels, the data, then CPU will just check if the current user has the kernel's data, access to the kernel's data or not. However, the data access is speculatively executed at the same time as the hardware security check. So hence the data may be leaked in the cache. So these are, the problems or vulnerabilities. So what are the best solutions for this meltdown and spectro? Means there is a software solution usually have a high performance in cost, but after the whole reasons to do the speculative execution for better performance, there some tools will be developed to check the security checks. And another the solution is the hardware solutions, which are the elusive. But during the chip manufacturers, they have proposed or released some solutions for certain variants of meltdown and spectrum. But however, there is no general solution provided in the chip manufacturers. So hardware solutions are most likely come with the performance penalty, like if Dennard scaling is still alive, then we may be in a much better situation to do that. So with this, the speculative execution topic completes, and we'll try to enter into the next topic we call the